These two nuclear power plants were built during the same era. Both used Generation III reactors. Both required thousands of workers, billions of dollars, years of construction. And yet, their construction stories could hardly have been more different. Why? Was it regulation, financing, the reactor design, or something else entirely? Over the last 2 episodes, we tested every major hypothesis. None of them fully explained what we observed. So perhaps we've been asking the wrong question. Not, why do some nuclear projects fail? But why do some nuclear programs succeed? Because once we changed the question, the answer wasn't hiding in a single project. It was hiding in the system all along. In the last episode, we tested the most common explanations for nuclear construction delays. Regulation, financing, reactor design, each one explained part of the picture. But none of them explained the whole picture. At first, that felt disappointing because we wanted a simple answer. One cause, one explanation. One thing we could point to and say, that's the problem. But engineering rarely works that way, especially when a project depends on thousands of workers, hundreds of suppliers, decades of accumulated experience. So perhaps the problem was never the evidence. Perhaps it was the question. Why do some nuclear programs repeatedly succeed, while others struggle to repeat that success? That question reveals a different pattern, because instead of searching for one cause, we begin searching for a system. And once we started looking at the evidence that way, something remarkable appeared. The projects hadn't changed, only the way we were looking at them had. For decades, most discussions about nuclear construction have focused on individual projects. One reactor, one budget, one construction schedule, one delay. It seems logical. Projects are built one at a time, so naturally, we evaluate them one at a time. But what if that's exactly where our understanding begins to break down? Because nuclear power plants are never built in isolation. Every project inherits something from the projects that came before it. Experienced engineers, qualified suppliers, mature regulatory institutions, lessons learned, manufacturing capability, construction methods, lessons learned. And that means every new reactor is influenced not only by its own design, but by the industrial ecosystem surrounding it. This changes how we interpret success. Instead of asking, was this project successful? We begin asking, what kind of industrial system produced this project? Because projects are temporary. Industrial capability is cumulative, and over time, that difference begins to shape every project that follows. At first glance, these projects appear remarkably similar. Both began in the 21st century. Both used Generation III reactor technology. Both required enormous financial investment, thousands of workers, years of construction. But if we stop looking at the reactors and begin looking at the systems behind them, a different picture begins to emerge. Neither project was built by a reactor. Both were built by industrial ecosystems. One ecosystem had the advantage of building the same design repeatedly, developing suppliers, training workers, and improving with every unit. The other faced a far more different challenge: rebuilding capabilities, recovering experience, reconnecting an industrial network that had weakened over time. The lesson is not that one project was destined to succeed or that another was destined to struggle. The lesson is much deeper. Large engineering projects reflect the capabilities of the systems that produce them. Once we see that, the projects themselves become easier to understand. Because the real story was never inside the reactor, it was always around it. If every project is part of a larger industrial system, then the next question becomes obvious. What do successful systems have in common? The answer is not one technology, not one regulation, not one financing model. Instead, the evidence points toward a collection of shared characteristics. Successful nuclear programs rarely treat each project as an entirely new beginning. They build, then build again and again. Each project transfers knowledge to the next. Workers become more experienced, suppliers become more capable, construction teams become more efficient, engineering organizations become more predictable. The system itself learns. This is one of the most powerful ideas in engineering. Experience does not remain inside people. It becomes embedded in organizations, in supply chains, in manufacturing, in construction practices. Over time, that accumulated capability changes the performance of future projects. Not because future projects become simpler, but because the system becomes better prepared. And perhaps that is the biggest lesson of all. Successful nuclear construction is not simply about building reactors. The product isn't just the reactor. The product is the capability to build the next one. At this point in the analysis, we are no longer asking what might matter. We are looking at what consistently appears. Across successful and struggling nuclear programs, certain factors appear again and again, not as isolated causes, but as recurring conditions. In the most successful cases, these elements are not optional. They are deeply embedded in the system before construction even begins. Continuity of construction appears to play a central role. Programs that build reactors in sequence tend to perform differently than programs that restart from scratch each time. Standardization also emerges as a critical pattern. When designs, components, and procedures remain stable, the system has room to learn. Supply chains behave similarly. They are not simply vendors, they are part of the learning system. When supply chains are stable, performance improves over time. When they are fragmented, variability increases. And perhaps most importantly, experience does not stay isolated within individuals. It accumulates within organizations, within institutions, within entire industries. What becomes clear is that no single factor explains success, but certain combinations appear far more often in high-performing programs. And when we step back, a pattern becomes visible. Successful nuclear programs are not defined by one advantage, they are defined by alignment. Alignment across the system creates stability, and stability creates learning, and learning creates performance. And what we call success is often just the result of alignment that has been built long before we ever see the project begin. This is Reactor Atlas, exploring nuclear energy through physics, not fear.